In chemistry, a ketone (Ketoone) is an organic compound with the structure RCR, where R and R can be a variety of carbon-containing substituents. Ketones and aldehydes are simple compounds that contain a carbonyl group. They are considered simple because they do not have reactive groups like -O or -Cl attached directly to the carbon atom in the carbonyl group, as in carboxylic acids containing -COOH. Many ketones are known and many are of great importance in industry and in biology. Examples include many sugars and the industrial solvent acetone, which is the smallest ketone. Nomenclature and etymology. The word ketone derives its name from ഃkiːtoʊn, an Old German word for acetone. According to the rules of IUPAC nomenclature, ketones are named by changing the suffix -ane of the parent alkane to a -none. The position of the carbonyl group is usually denoted by a number. For the most important ketones, however, traditional non-systematic names are still generally used, for example acetone and benzophenone. These non-systematic names are considered retained IUPAC names, although some introductory chemistry textbooks use systematic names such as 2-propanone or PROPAN21 for the simplest ketone instead of acetone. The common names of ketones are obtained by writing separately the names of the two alkyl groups attached to the carbonyl group, followed by ketone as a separate word. The names of the alkyl groups are written alphabetically. When the two alkyl groups are the same, the prefix -di is added before the name of alkyl group. The positions of other groups are indicated by Greek letters, the alpha carbon being the atom adjacent to carbonyl group. If both alkyl groups in a ketone are the same, then the ketone is said to be symmetrical, otherwise unsymmetrical. Although used infrequently, oxo is the IUPAC nomenclature for a ketone functional group. Other prefixes, however, are also used. For some common chemicals, keto or oxo refer to the ketone functional group. The term oxo is used widely through chemistry. For example, it also refers to an oxygen atom bonded to a transition metal. Structure and properties. The ketone carbon is often described as sp2 hybridized, a description that includes both their electronic and molecular structure. Ketones are trigonal planar around the ketonic carbon, with C-C-O and C-C-C bond angles of approximately 120 degrees. Ketones differ from aldehydes in that the carbonyl group is bonded to two carbons within a carbon skeleton. In aldehydes, the carbonyl is bonded to one carbon and one hydrogen and are located at the ends of carbon chains. Ketones are also distinct from other carbonyl-containing functional groups, such as carboxylic acids, esters and amides. The carbonyl group is polar because the electronegativity of the oxygen is greater than that for carbon. Thus, ketones are nucleophilic at oxygen and electrophilic at carbon. Because the carbonyl group interacts with water by hydrogen bonding, ketones are typically more soluble in water than the related methylene compounds. Ketones are hydrogen bond acceptors. Ketones are not usually hydrogen bond donors and cannot hydrogen bond to themselves. Because of their inability to serve both as hydrogen bond donors and acceptors, ketones tend not to self-associate and are more volatile than alcohols and carboxylic acids of comparable molecular weights. These factors relate to the pervasiveness of ketones in perfumery and as solvents. Classes of ketones. Ketones are classified on the basis of the substituents. One broad classification subdivides ketones into symmetrical and asymmetrical derivatives, depending on the equivalency of the two organic substituents attached to the carbonyl center. Acetone and benzophenone C6H5 asymmetrical ketones. Acetophenone CH3 is an asymmetrical ketone. In the area of stereochemistry, asymmetrical ketones are known for being prochiral. Diketones. Many kinds of diketones are known, some with unusual properties. The simplest is diacetyl CCH3, once used as butter flavoring in popcorn. Acetylacetone is virtually a misnomer because this species exists mainly as the monoenol CH3 CCH equals CCH3. Its enolide is a common ligand in coordination chemistry. Unsaturated ketones. Ketones containing alkene and alkene units are often called unsaturated ketones. The most widely used member of this class of compounds is methyl vinyl ketone CH3CCH equals CH2, which is useful in the Robinson annulation reaction. Lest there be confusion, a ketone itself is a site of unsaturation, that is, it can be hydrogenated. Cyclic ketones. Many ketones are cyclic. The simplest class have the formula NCO, where N varies from 3 for cyclopropanone to the teens. Larger derivatives exist. Cyclohexanone, a symmetrical cyclic ketone, is an important intermediate in the production of nylon. Isophorone, derived from acetone, is an unsaturated asymmetrical ketone that is the precursor to other polymers. Muscone, 3-methylpentadecanone, is an animal pheromone. Another cyclic ketone is cyclobutanone, having the formula C4H6O. Ketone-enol tautomerization. Ketones that have at least one alpha hydrogen undergo ketone-enol tautomerization. The tautomer is an enol. Tautomerization is catalyzed by both acids and bases. Usually, the keto form is more stable than the enol. This equilibrium allows ketones to be prepared via the hydration of alkanes. Acidity of ketones. Ketones are far more acidic than a regular alkane. This difference reflects resonance stabilization of the enolate ion that is formed upon deprotonation. The relative acidity of the alpha hydrogen is important in the enolization reactions of ketones and other carbonyl compounds. The acidity of the alpha hydrogen also allows ketones and other carbonyl compounds to undergo nucleophilic reactions at the position, with either stoichiometric and catalytic base characterization. An aldehyde differs from a ketone because of its hydrogen atom attached to its carbonyl group, making aldehydes easier to oxidize. Ketones don't have a hydrogen atom bonded to the carbonyl group, and are more resistant to oxidation. They are only oxidized by powerful oxidizing agents which have the ability to cleave carbon-carbon bonds. Spectroscopy. Ketones and aldehydes absorb strongly in the infrared spectrum near 1700 cm-1. The exact position of the peak depends on the substituents, whereas 1-HNMR spectroscopy is generally not useful for establishing the presence of a ketone. 13-CNMR spectra exhibit signals somewhat downfield of 200 ppm depending on structure. Such signals are typically weak due to the absence of nuclear Overhauser effects. Since aldehydes resonate at similar chemical shifts, multiple resonance experiments are employed to definitively distinguish aldehydes and ketones. Qualitative organic tests. Ketones give positive results in Brady's test, the reaction with 2,4-dinitrophenylhydrazine to give the corresponding hydrazone. Ketones may be distinguished from aldehydes by giving a negative result with Tollen's reagent or with Fehling's solution. Methyl ketones give positive results for the iodifum test. Synthesis. Many methods exist for the preparation of ketones in industrial scale and academic laboratories. Ketones are also produced in various ways by organisms. See the section on biochemistry below. In industry, the most important method probably involves oxidation of hydrocarbons, often with air. For example, 1 billion kilograms of cyclohexanone are produced annually by aerobic oxidation of cyclohexane. Acetone is prepared by air oxidation of cumin. For specialized to small-scale organic synthetic applications, ketones are often prepared by oxidation of secondary alcohols. R2CH plus OR2C equals O plus H2O. Typical strong oxidants include potassium permanganate or a Cr compound. Milder conditions make use of the Des-Martin periodinane of the Moffatt-Swen methods. Many other methods have been developed. Examples include bigeminal halide hydrolysis, bihydration of alkanes. Such processes occur via enols and require the presence of an acid and mercury 2-sulfate. Subsequent ENOL ःkietotomerization gives a ketone. This reaction always produces a ketone, even with a terminal alkane. From Weinreb amides using stoichiometric organometallic reagents. Aromatic ketones can be prepared in the Friedel-Crafts acylation, the related Huben-Hoesch reaction, and the Fries rearrangement. Ozonolysis and related dihydroxylation oxidative sequences cleave alkenes to give aldehydes and/or ketones, depending on alkene substitution pattern. In the Kornblum-Delamere rearrangement, ketones are prepared from peroxides and base. In the Ruzicka cyclization, cyclic ketones are prepared from dicarboxylic acids. In the NEF reaction, ketones form by hydrolysis of salts of secondary nitro compounds. In the Fukuyama coupling, ketones form from a thioester and an organozinc compound by the reaction of an acid chloride with organocadmium compounds or organocopper compounds. The Dakin-West reaction provides an efficient method for preparation of certain methyl ketones from carboxylic acids. Ketones can also be prepared by the reaction of Grignard reagents with nitriles, followed by hydrolysis. By decarboxylation of carboxylic anhydride, ketones can be prepared from haloketones in reductive dehalogenation of haloketones. In ketonic decarboxylation, symmetrical ketones are prepared from carboxylic acids. Oxidation of amines with iron chloride, hydrolysis of unsaturated secondary amides, beta-ketoacid esters, or beta-diketones. Acid-catalyzed rearrangement of 1,2-diols. Reactions. Ketones engage in many organic reactions. The most important reactions follow from the susceptibility of the carbonyl carbon toward nucleophilic addition and the tendency for the enolates to add to electrophiles. Nucleophilic additions include in approximate order of the generality. With water gives geminal diols, which are usually not formed in appreciable amounts. With an acetylide to give the alpha-hydroxyalkene. With ammonia or a primary amine gives an amine. With secondary amine gives an enamine. With Grignard and organolithium reagents to give, after aqueous workup, a tertiary alcohol. With an alcohols or alkoxides to give the hemiketal or its conjugate base. With a diol to the kettle. This reaction is employed to protect ketones, with sodium amide resulting in C-C bond cleavage with formation of the amide RCONH2 and the alkane RH, a reaction called the Haller-Bauer reaction, with strong oxidizing agents to give carboxylic acids. Electrophilic addition reaction with an electrophile gives a resonance-stabilized cation, with phosphonium ylides in the Wittig reaction to give the alkenes. with thiols to give the thioacetyl, with hydrazine 1 di-substituted derivatives of hydrazine to give hydrozones, with a metal hydride gives a metal alkoxide salt, hydrolysis of which gives the alcohol, an example of ketone reduction, with halogens to form an alpha-haloctone, a reaction that proceeds via an ENOL, with heavy water to give an alpha-deuterated ketone. Fragmentation in photochemical Norrish reaction. Reaction of 1,4-aminodiketones to oxazoles by dehydration in the Robinson-Gabriel synthesis. In the case of aryl alkyl ketones, with sulfur and an amine give amides in the Wilgerot reaction, with hydroxylamine to produce oximes, with reducing agents to form secondary alcohols, with proxy acids to form esters in the Bereyer-Villiger oxidation. Biochemistry. Ketones are pervasive in nature. The formation of organic compounds in photosynthesis occurs via the ketone ribulose-1,5-bisphosphate. Many sugars are ketones, known collectively as ketoses. The best-known ketose is fructose, which exists as a cyclic hemiketal, which masks the ketone functional group. Fatty acid synthesis proceeds via ketones. Acetoacetate is an intermediate in the Krebs cycle which releases energy from sugars and carbohydrates. In medicine, acetone, acetoacetate, and beta-hydroxybutyrate are collectively called ketone bodies, generated from carbohydrates, fatty acids, and amino acids in most vertebrates, including humans. Ketone bodies are elevated in the blood after fasting, including a night of sleep, in both blood and urine, in starvation, in hypoglycemia, due to causes other than hyperinsulinism, in various inborn errors of metabolism, and intentionally induced via a ketogenic diet, and in ketoacidosis. Although ketoacidosis is characteristic of decompensated or untreated type 1 diabetes, ketosis or even ketoacidosis can occur in type 2 diabetes in some circumstances as well. Applications. Ketones are produced on massive scales in industry as solvents, polymer precursors, and pharmaceuticals. In terms of scale, the most important ketones are acetone, methylethyl ketone, and cyclohexanone. They are also common in biochemistry, but less so than in organic chemistry in general. The combustion of hydrocarbons is an uncontrolled oxidation process that gives ketones as well as many other types of compounds. Toxicity. Although it is difficult to generalize on the toxicity of such a broad class of compounds, simple ketones are, in general, not highly toxic. This characteristic is one reason for their popularity as solvents. Exceptions to this rule are the unsaturated ketones such as methyl vinyl ketone with LD50 of 7 mg per kilogram.